Hi everybody. In this lecture we're going to take a more in-depth look at the simple harmonic oscillator. So if this is your first time looking at one of these lectures of mine, bear in mind there's some older lectures on simple harmonic oscillator which introduce you to the solution to the differential equation. And so if you haven't seen those lectures, then you'll probably want to go back and look at those before we get into this one. Okay, so that aside, one of the things that I wanted to focus on in this lecture is how to deal with it when we have a mass on a spring that is under the influence of gravity. So previously, the masses on springs that we dealt with horizontal masses on springs, and you didn't really have to include that in the solution of the sum of the forces because the gravity was then perpendicular to the acceleration of the spring. But here I want to look at vertical masses on springs. So a mass hanging from a vertical spring, I should say hanging, or atop a vertical spring. So in here I'm talking about, in this case, we have a mass hanging from a spring that's suspended from, say, a ceiling, but it could very also easily be talking about the situation where you have, for example, a table, and the spring is attached to the table and sticking straight upward, and the mass is attached to that. So you might see problems with either of those configurations here. Now, if it's hanging like this one, then what will happen is that the spring will stretch out due to the force of gravity pulling on the mass, pulling it down. Okay? Now, if you have a vertical mass on a spring sitting on a table where the spring is sticking up, then what will happen is the force of gravity will compress the spring and push it down a little bit. Okay? So either way, I'm going to do here a hanging mass, but I think you'll see that the displacement from equilibrium will give you the same equation either way. So here we go. We've got the hanging mass, and in this case, the mass on the spring is not oscillating. It's just being stretched out under due to the force of gravity acting on it, and it's just sitting there. Okay, so this is a non-oscillating case. If that is stationary, then what happens is the sum of the forces acting on, for example, here, this ball, will sum to 0. And so if you draw the free body diagram for what's going on, you have mg acting down, that's my yellow arrow, and then you have the spring force acting upward. Remember, our spring force is Hooke's law, which is minus k, the spring constant, times the displacement of the object from its equilibrium position. Okay, so here that is acting upward. Now, if we look at just the y component, all we have here is y components anyway, and in this problem it's more convenient to have the y-axis, positive y pointing down. Okay, it's just more convenient for this problem. Then if you say the sum of the forces is equal to 0, as it is for any non-accelerating mass, then you have mg acting down. If it's down is positive, then mg would be positive, and then you have the spring force acting upward, which in this case would be negative, so the negative k delta y there. Now, solving then for the extension of the spring, due to the pull of gravity, you can see that it will stretch the spring out by some amount delta y, which would be equal to mg over k, the weight of the object, divided by the spring constant. Now, in Matter and Interactions, our textbook, they refer to this displacement of the spring from its equilibrium position due to the stretch of gravity or the compression of gravity. They call it y sub I, and that is the new equilibrium position for the mass on a spring if it starts to oscillate. Okay? So if you put the origin at the spring's unstretched length, then the new equilibrium position will be displaced by an amount yi. Okay, so that's a stationary mass on spring, but that's not very interesting, right? Of course, the whole point of a spring is oscillation. So now let's let that mass on the spring oscillate. Now, when the mass on the vertical spring oscillates, it's going to oscillate about that new equilibrium point yi. It will not oscillate about the unstretched length of the spring. And if you don't believe me, you should just go do this experiment for yourself. If you attach a mass to a spring, it'll drop it down, for example, if you let it dangle, and then you give it a little push, and it'll oscillate about that drop down point. Okay? When it's oscillating, it's still subject to those two forces, which are gravity and the spring force. But now we have the equation as follows for the sum of the forces in y, you're going to get the mass times the acceleration. Since it's moving, there will be an acceleration now if it's oscillating, and then that will equal to mg minus ky. Now, this y coordinate will be the sum of that offset point mg over k plus what I'm going to call y prime. Now, y prime I'm going to call the wiggle coordinate, okay? So what's going to happen here is the object is going to have some constant offset due to gravity, and then it'll also wiggle about that point with some amplitude y prime. So summing that, those two forces there, you have mg minus ky, which is mg minus k times mg over k plus y prime, right? Then you can see that if you multiply through in this expression by k, you get mg minus mg over k times k minus ky prime. And so then those mg's cancel each other out, mg minus mg, and they cancel out, and you're just left with minus ky prime. Now, this is the same differential equation, basically. Ma is equal to minus ky prime. This is the same differential equation that we solved before for a mass on a horizontal spring. Excuse me. So the equation of motion for the wiggle coordinate will be the same as the mass on a horizontal spring. And gravity then is just that constant offset. And since we're looking at a not constant type motion, the constant offset will go away. So we solved this differential equation before. I'm not going to go through the solution to the differential equation here. Again, I urge you to look back at those lectures for that. And so instead, I'm just going to present the solutions that we solved before in our previous lecture here as the solution to our y prime. So here, y prime of t is a cosine omega t plus phi. Now let me define my terms. Here, a is the amplitude of oscillation. Omega is the angular frequency. Okay, and remember before we used the definition that the angular frequency omega is equal to the square root of k over m, the square root of the spring constant divided by the mass. And then we have t, of course, it's dependent upon time t, and then we have phi, which is the phase constant. And that's just basically where you start your clock, okay? So that is our equation for our wiggle coordinate, y prime, and it describes the bobbing of the mass back and forth about the equilibrium point. Now, if you want the velocity and the acceleration, you take the derivatives of that function y prime of t. So the first order derivative of y prime of t will give you the velocity in the y direction due to the oscillation. So that'll be vy of t, which is minus a omega sine omega t plus phi. And then you can take the time derivative of the velocity to get the acceleration. And that would give you the acceleration in the y direction is minus a omega squared cosine of omega t plus phi. All right, so this is exactly the same differential equation and hence exactly the same solutions that we previously covered. Okay, so let's start out by doing a simple example problem. This is a little bit more complex than the simple harmonic motion problems that we've done before, but still it's not as complex as the last example we're going to do. So let's do this example problem. So let's read this together. An 83 kilogram student hangs from a bungee cord that has a spring constant of 270 newtons per meter. The student is pulled down to a point where the cord is 5 meters longer than its unstretched length and released. Describe the motion. Where is the student and what's their velocity 2 seconds later? Okay, and this is from our textbook Matter and Interaction. So I've drawn a little sketch here to help us visualize what's going on. So here on the far right of my sketch, I've got my unstretched length of my cord shown right here, okay? And then I've defined where my origin is. So yet again, I'm going to take my y coordinate plus y being down, and then these big arrows right here just represent my origin of my coordinate system, which I put at the end of my unstretched length of my cord. Okay, now, what it says in the problem is that the student is pulled down to a point where the cord is 5 meters longer than its unstretched length. So what I've got here is on the far left a white bar showing how far down it's pulled when you first start. Okay. Now from our discussion previously, we understand that what will happen is that our student, which is represented here by this creepy looking hanged face because I'm a terrible artist. So our student in the smiley here is going to bob up and down about their new equilibrium position, which is displaced from the unstretched length because of the stretch of the spring due to gravity, right, of the mass, pulling the mass. So I'm going to call my wiggle coordinate y prime, and I'm going to draw it here, okay? So that's how it's going to bob back and forth, right? Now, if we're describing the motion, it would be really good to solve for what the new equilibrium point is for this motion. So step number 1, our yi, which is our new equilibrium point, is equal to mg over k. So that would be 83 kilograms the mass times 9.8 meters per second squared, the acceleration due to gravity, divided by 270 newtons per meter. And when you solve that, you get 3 meters, okay? So I've drawn that here in this bar, this white bar right here on the right next to my coordinate system. I've shown my yi is 3 meters below the unstretched length, okay? So that's where the equilibrium position is, so that's where I put my creepy looking smiley face head, all right? And then what's going to happen is the student is going to bob about that equilibrium position, 3 meters. And I've indicated that with this double-sided arrow to indicate up and down motion in my wiggle, okay? All right, now we can solve right away for our new amplitude, or for our amplitude of oscillation A of this student. So what's happened is, it says the student's pulled down to a point where the cord is 5 meters longer and then released. So I'm interpreting that to mean that they weren't pushed, they were just pulled down and then released from rest, okay? So if that's the case, then that will be the lowest point that the student hits in their up and down bobbing motion, okay? So since our new equilibrium position is 3 meters and the max downward displacement from equilibrium is 5 meters, then that means that the amplitude of oscillation of the student will be 5 meters minus 3 meters, which is 2 meters. So I've solved for our amplitude, A, okay, and that's step number 1 in getting to our equation of motion for this student. Okay, so our equation of motion is y prime of t is a cosine omega t plus phi. We've solved for A. So the next thing in the equation that we need to identify is omega, which is our angular frequency. Okay, now in a previous lecture we developed the idea that omega, the angular frequency, is equal to the square root of k over m, and that came from the solution of our differential equation. So the square root of k over m, k is 270 newtons per meter, and then the mass of the student is 83 kilograms. So if we take the square root of 270 divided by 83, we get 1.8 radians per second for our angular position, or our angular frequency. So that's what we plug into our equation here, a cosine omega t plus phi. All right, now we need to solve for our phase constant phi, and to do that, what we do is we use our initial conditions for the motion. So what I mean by that is at t is equal to 0, for example, let's start our clock when we release the student after pulling it down, right? So we're going to pull the student down, we're going to release them from rest, and we're going to call that point when we release them as t equal to 0. So if that's the case, then we can plug into our equation so far, right? If t is equal to 0 when we start, then we would have a cosine omega t plus phi. The omega t part would be 0 because t is equal to 0, and then we would just have y prime is equal to a cosine phi. Okay, so at the point where we release them, they are at their max downward displacement. Okay, so if we're referencing the new equilibrium point, which is at 3 meters, then they are 2 meters below that. Now, we said down was positive, so that means that their position at t is equal to 0 is plus 2 meters. So that's what we plug in for y prime of t. Now, y prime of t is equal to a cosine phi. So a is 2 meters. And then, since t is 0, the only thing that we have left in that argument is cosine of phi, all right? Okay, now we can then solve this equation for phi by dividing both sides by 2 meters and then taking the inverse cosine, or the arc cosine. And when we do that, we get phi is equal to the inverse cosine of 1, because we have 2 over 2. So phi would be equal to the inverse cosine of 2 over 2, which is 1. When you solve that, of course, you get a phase constant of 0. All right? Okay, so that means that our equation of motion in this case is y prime of t is equal to, now this is for a random time, 2 meters times the cosine of 1.8 radians per second times t. That's our equation of motion. Now this is the equation of motion for our wiggle coordinate. If you want to figure out what the y coordinate would be with respect to the origin that I showed in this figure here, where you have the origin here, then you have a constant offset from your wiggle coordinate, right? So your total position y would be equal to y prime plus yi, which is your y prime is yi is 3 meters, and then plus your y prime, which is 2 meters cosine 1.8 radians per second times t. So that describes the motion in a mathematical way, I think, pretty fully. Okay, now the rest of the question asks, where is the student and what is their velocity 2 seconds later? Okay, great. So we're going to use the equation that we developed for any random time t on the previous slide and plug in for that at t is equal to 2 seconds. And that's how we solve for where is the student. So 3 plus 2 times the cosine of 1.8 radians per second times 2 seconds gives me 3 minus 1.78 meters, and that's 1.22 meters. So a way to describe it would be that the student is 1.22 meters below the unstretched position of the cord. All right, now, what's their velocity? Remember that to get the velocity, you take the time derivative of the position. So Vy of t is minus a omega sine omega t plus phi. Remember that you're not going to have any additive constants here because you're taking a derivative. So the yi part of it does not contribute because the time derivative of yi is 0 because it's a constant. So here we have Vy of t is minus a omega sine omega t plus phi. Plugging in for all of that, a is 2 meters, omega is 1.8 radians per second, and t is 2 seconds. So plugging in for all of that, I end up with V is equal to plus 1.6 meters per second. Now here, plus Y is down, so that means that the student is traveling 1.6 meters per second downwards at T is equal to 2 seconds. Okay? All right, so that's our first example problem for a vertical mass on a spring. Now, we also want to know how to describe it if a system is not released from rest. So all of our examples to date in this class have been discussing what happens if you pull something down or push it up or compress the spring in some way and then let it go without giving it an initial velocity. But if you do give it an initial velocity, then that changes things a lot. And the reason is, of course, that if you give it an initial velocity, you've added energy to the system. Okay, and as we'll see when we explore later, the amplitude of oscillation is proportional to the energy of the system. Okay, specifically, the energy is proportional to the amplitude squared. So the amplitude will actually increase as the energy of the system increases. And so if you give it a push as you release it, you're adding energy to the system, your amplitude will be bigger. It's also going to change the phase constant because if you give it a push and you're not releasing it at one of the extrema, then what's going to happen is it'll be like the object is in the middle of its motion somewhere at some random time in the motion, not starting at one of the extreme endpoints. And so that complicates a little bit solving for the phase constant. And so what I'd like to do in these next slides is develop a formula that you can use to solve for the amplitude and the phase constant for any situation. Okay, so what you're going to do is your amplitude and phase constant will be functions of the initial conditions of your system. So let's go back to horizontal masses on springs, but it doesn't matter if it's horizontal or vertical. Okay, it really doesn't. It's the same kind of formula. We're going to say that you have some initial position, some initial velocity at some random time, okay, because I want to keep it as general as possible. So we're going to call our initial position x naught, our initial velocity v naught, and the random time t naught, okay? So if I'm to write what my position and velocity equations would look like for those initial conditions, then I would say that x naught is equal to a cosine omega t naught plus phi, right? And V naught is equal to minus A omega sine omega T naught plus phi. Okay? So what we want is to be able to express A and phi in terms of these initial conditions. Well, in a proof with sinusoidal functions, there's usually two things that, jump straight to your head every time you start one of these proofs. One is to exploit the trig identity that sine squared plus cosine squared is 1. Okay, so that's always one thing that you think. And then another thing is to use the definition of some other trig identity. So for example, we've got a sine and a cosine, and that begs me to make a tangent somehow. Okay, now we're going to do both of those things when we talk about finding the amplitude and the phase constant. Let's use the sine squared plus the cosine squared equals 1 trig identity first. Okay? So here I have x naught is equal to a cosine omega t naught plus phi. If I square that, then I'll have a cosine squared term. So that gives me x naught squared is equal to a squared cosine squared omega t naught plus phi. If I square my v naught, then I'll have a sine squared of phi, or a sine squared term. So v naught squared is equal to a squared omega squared sine squared omega t naught plus phi. All right? Now, I want to exploit my identity cosine squared plus sine squared is 1. So what I'm going to do is I'm going to divide, say for example, this x naught squared is equal to a squared cosine squared. I'm going to divide out by a squared, and that'll just give me my cosine squared term. So if I solve for that, cosine squared omega t naught plus phi is going to equal to x naught squared over a squared. Now if I isolate my sine squared omega t naught plus phi is v naught squared over a squared omega squared. Now I just sum these sine squared and cosine squared terms, and that gives me 1. So cosine squared plus sine squared is 1, right? And that is equal to x naught squared over a squared plus v naught squared over a squared omega squared. Okay? Now you can see right away, if you look here, I've got now everything with a in it as a function of my initial conditions and my angular frequency. And that's what I want. So now I can solve for a pretty easily. I've got 1 is equal to x naught squared over a squared plus v naught squared over a squared omega squared. I can multiply everything through by a squared, and I have a squared is equal to x naught squared plus v naught squared over omega squared. Take the square root, and I'm done. A is equal to the square root of x naught squared plus v naught squared over omega squared. Okay? Now let's think about this for just a second. If you have not given the system some initial velocity, if the initial velocity is 0, in other words, if you're just releasing it from rest as we did in our previous example, then the initial displacement that you give it, x naught, would be equal to your amplitude. And that's the kind of problems that we've worked to date. However, if you give it some initial velocity, you're going to see the amplitude increase, and that's reflected in this equation. All right, now let's talk about how to find the phase constant phi. To find the phase constant, we're going to use the other method that I used, that I discussed for doing trigonometric proofs. We're going to take that sine and cosine, we're going to divide them, or we're going to make a tangent, right? I mean, one of those two things should pop into your head every time. If you get assigned some kind of proof problem, it's got sines and cosines in it, give it a try. Maybe it'll work, right? Okay, so what we're going to do is if we divide the sine by the cosine to make a tangent, that means that we've got to divide v naught by x naught. So v naught is equal to minus a omega sine omega t naught plus phi. We're going to divide that by x naught, a cosine omega t naught plus phi. If we do that, then the a will cancel out from the top and the bottom of that equation, and I'm left with minus omega tangent omega t naught plus phi. Okay? Now, rearranging my equation with just some simple algebra, I'm going to divide both sides by minus omega. So then I have tangent omega t naught plus phi is equal to v naught divided by minus omega x naught. So you can see here, if I just take the inverse tangent of both sides, or the arc tangent of both sides, then now I have an equation with my initial conditions for phi, and I'm good to go. So here, taking the inverse tangent, I've got on the left-hand side, omega t naught plus phi is equal to, on the right-hand side, the inverse tangent of v naught over minus omega x naught. So now, just subtracting omega t naught from both sides, I have an expression for the phase constant, and that's equal to the inverse tangent of v naught over minus omega x naught minus omega t naught. Okay? Of course, if your initial time is t is equal to 0, the second term disappears. All right, and that makes it even simpler. Okay, now that I've developed these expressions for how to handle the amplitude and the phase constant for more complex problems where you give an initial velocity, let's do an example problem together. In this one, which is kind of a modified problem from matter and interactions, we have a ball of mass 20 grams hanging from a vertical spring whose relaxed length is 20 centimeters and whose stiffness is 0.9 newtons per meter. At t is equal to 0, the spring is pulled down by 5 centimeters and given an initial velocity of 1 meter per second. Write the equation of motion and describe the motion. All right, so here we go. First of all, let's find what our new equilibrium position is for this mass on a spring. It tells me that the relaxed length is 20 centimeters, but that's when it's not got anything attached to it with gravity pulling it down. So solving for my new yi, I get mg over k is equal to yi, which is 0.02 kilograms times 9.8 meters per second squared divided by 0.9 newtons per meter. When I do all that, I get yi is equal to 0.218 meters. So this would mean, to interpret this result, that the new equilibrium position is 21.8 centimeters below the unstretched length. Now, since the relaxed length is 20 centimeters, if I think of having a ceiling up here and having my spring dangling down, right, that would mean that if I put my origin at the ceiling where I'm hanging it, that my mass would be 41.8 centimeters below the attachment point of the spring, because I've got 20 centimeters for the unstretched length, and then I add on 21.8 centimeters for the stretch when the mass is attached. I hope that's clear. Okay, now to describe the motion, I need to write my equation of motion, right? So I've got y prime is equal to a cosine omega t plus phi. So I've got my omega is equal to the square root of k over m. And so that's going to be the square root of 0.9 newtons per meter divided by 0.02 kilograms, which gives me an angular frequency of 6.7 radians per second for this problem. Now, since the thing has been given an initial velocity, I can't just say that it's 0.05 meters below, right? It's going to have a larger amplitude of oscillation than that because I've added energy to the system by giving it a push. So my amplitude will then be equal to the square root of y naught squared plus v naught squared over omega squared. Here, remember, we had an x naught before for horizontal motion. Y naught is what the position is with respect to the new equilibrium position at t is equal to whatever the starting time is. So here it's y naught because we're moving in the y direction. So it said in the problem that it is pulled downward by 5 centimeters. Okay, so that is going to be from its stretched out new equilibrium position. It's going to hang and then you're going to pull it down 5 centimeters and you're going to let it go. So that means that my y naught is 0.05 meters, okay, which is then squared. And then plus v naught squared over omega squared. So that's 1 meters per second squared divided by 6.7 radians per second, and then I square it. Now when I plug all that into my calculator, I get an amplitude of oscillation of 0.157 meters, or 15.7 centimeters. So you see, this verifies what we've been saying before. If you give it an initial velocity, you've added energy to the system, and this will increase the amplitude. If we had released this sucker from rest, it would have an amplitude of oscillation of just 5 centimeters, because that's how far down we pulled it. Okay, next we're going to solve for the phase constant phi. The phase constant, the formula that we developed, is the inverse tangent of v naught over negative omega y naught minus omega t naught. Now, we're starting our clock at t is equal to 0 when we pull the thing down and then give it a release, right? So that means that this omega t naught term goes to 0, and then we just have the inverse tangent of 1 meter per second over negative 6.7 radians per second divided by 0.05 meters, okay? When I take that inverse tangent, I get negative 1.25 radians. Remember, it's very important that when you plug things into your calculator here that everything be in radian mode. If you have it in degree mode, you're going to get weird things, okay, for these kinds of problems. So this is negative 1.25 radians. So my equation for my wiggle coordinate, which is going to be y prime of t, will be a cosine omega t plus phi, which is, in this case, 0.157 meters times the cosine of 6.7 radians per second t minus 1.25 radians. So that's our equation of motion for the wiggle. Now, if you wanted to talk about the y-coordinate of the mass, and let's say, for example, that you put your y-coordinate at the ceiling, then what you would need to do is add your constant offset to the wiggle coordinate. So that would be, in this case, if the coordinate is at the ceiling, the unstretched length of the spring plus the stretch due to the downward pull of gravity, which is a constant offset. Remember, that was 20 centimeters plus 21.8 centimeters. So my equation of motion for y of t is 41.8 centimeters, or 0.418 meters, plus my wiggle coordinate, 0.157 meters times the cosine of 6.7 radians per second t minus 1.25 radians. Okay? So, I think the way that we do things in physics, right, is that we learn things the first time, say in a 1000 level physics class at one level, right? And then you come back and you look at it again and you look at it deeper. And then you come back and you look at it again and you look at it deeper. So I can promise you that if you're a physics student, by the time you get to your senior year, you're going to be like, how many times do I have to see the harmonic oscillator? And the answer is about 1 million, okay? So this is iteration, what are we on now? 3, 4, just in our class? All right, so you've got, 999,997 to go, okay? And with that happy idea, I'll end there. And let me know if you have any questions, and I'll see you in class.